关. Good afternoon, everyone. It's my great pleasure to be here to share with you my latest research work. My name is Nan Li. I come from the K-State Laboratory of Transducer Technology, Aerospace Information Research Institute, Chinese Academy of Science. And it's my first time to join IEEE sensors, and I'm so excited. Today, my topic is a magnetofluidic nucleic acid biosensor for multiplex pathogen detection, and my paper was luckily selected as a candidate for Best Paper Award. My presentation contains 3 parts. First comes the previous work. This slide shows my education experience. I graduated with a bachelor degree from Beijing Institute of Technology, majoring in automation. Then I earned a doctoral degree from Tsinghua University, majoring in biomedical engineering. In 2022, I joined in Aerospace Information Research Institute as a research assistant. As you can see, my educational journey has been characterized by a cross-disciplinary approach, which allowed me to integrate my expertise in engineering principles with applications in medical and healthcare domains. My advisor in Tsinghua University is Professor Chen, who is a member of Academician of Chinese Academy of Engineering. He established the Beijing National Engineering Research Center, and he led our group to invent various biochips and equipment. And he has won the 2nd prize of National Technology Invention Award twice. My collaborators in State Laboratory of Transducer Technology are Professor Junbo Wang and Professor Chen. They are experts in the field of pressure sensors and single-cell sensors. We have a MEMS process line that supports design, manufacture, and characterization of silicon chip-based sensors. This slide shows parts of my research results since my PhD. It mainly includes 2 aspects: the self-contained microfluidic system and the centrifugal microfluidic chip system, and my population are listed below. This slide shows demo of self-contained microfluidic system. Self-contained means the microfluidic system contains the pumps and valves necessary for microfluidic control. It can achieve magnetic beads-based nucleic acid extraction. And this step shows the magnetic beads washing for 3 times. Then comes the magnetic beads elution. Then distribute the elution buffer to 8 reaction chambers. We can simultaneously detect 8 targets. After thermal sealing the reaction chambers, we can program PCR. Finally, we diode channel fluorescence detection the results. And our work was selected as the back cover of lab-on chip. The second work is the centrifugal microfluidic-based system. This is for immunoassay detection. We can take a drop of our blood sample, and we integrate multi-steps to analyze for immunoassay, and we integrate the immunoassay lateral strips in our microfluidic chip. And for this work, our work was selected as the front cover of lab-on chip. We can control the steps very precisely. During COVID-19, I have participated in the development of the first fully integrated SARS-CoV-2 nucleic acid detection product approved in China. And our work was reported to the chairman of China. Below, I will briefly introduce this work. Molecular diagnostics especially refers to the analysis of biological markers such as DNA, RNA, using nucleic acid amplification method. molecular diagnostics plays a crucial role in many various fields, such as clinical diagnosis, forensic science, precise medicine, and genetic analysis. In this slide, let's have a closer look at molecular biology laboratory. Standardization of molecular amplification testing needs 4 isolated rooms to avoid pollution. It will cost a lot. Therefore, there is a big demand to construct some innovative, fully integrated nucleic acid analysis instruments that can solve clinical problems. A plenty of fully integrated nucleic acid analysis systems using microfluidic technology have been proposed, which can be characterized into 6 types by their fluid control strategies, such as pump and valve control, centrifugation, diaphragm pump valve control, electrowedding, just introduced by Professor Moon last section, and gravity driving, and also the magnetic fluidic control. This work is set by Professor Wang. And among these methods, the magnetofluidic control method is inexpensive and easy to fabricate. And this method transfers the fluidic handling to magnetic bead particle translocation. No need for pumps and valves. So I think it's preferred technology for point-of-care testing. However, multiplex detection cannot be achieved with existing magnetofluidic device because this method has no active fluid manipulation, and magnetic beads are difficult to disperse. So this is overview of my design, the nucleic acid biosensor. We can look at the picture. The magnetic-fluidic biosensor contains the main body of the cassette, which contains the lattice chamber, the connecting chamber, the washing chamber, and 6 reaction chambers arranged in a circle. And ultrasonic head groove in the center of this biosensor. The lattice chamber and the washing chamber are used to load lattice buffer containing magnetic beads and washing buffer respectively. The connecting channel is used to connect the lattice chamber and the washing chamber, and the PDMS is loaded to isolate the lattice chamber and the washing chamber. 6 reaction chambers under the washing chamber are used to load lamp mix and the PDMS. The PDMS is in the reaction chamber, can vertically divide the lamp reaction mixture and the washing buffer in the washing chamber. The main body of the biosensor is bonded with the cover plate by the double-sided tape. This is assembled cassette. In contrast to other magnetofluidic method, the stratification stability of multi-layer liquid inside the washing and the reaction chamber is essential for achieving multiplex detection with our biosensor to verify the variability of PDMS as an intermediate layer for isolating the washing buffer and the lamp master mix in the vertical direction. COMSOL multi-physics simulation were conducted using linear surface flow model. In the left figure, right figure illustrates that the half volume of the reaction chamber was filled with the lamp mix. In the middle is PDMS, and the above is the washing buffer. And the simulation result is consistent with the real experimental result. An ultrasonic field inside the washing chamber was performed by ultrasonic solid interaction model. Time-lapse sequence of magnetic beads dispersion inside the washing chamber proved the feasibility of this method. Distribution of magnetic beads was simulated using the magnetic field model. There were 6 magnets arranged in a circle with same polarity to its neighbor. This symmetrical magnetic force split and guide the magnetic beads to each center of the 6 magnets. Above simulation result were consistent with actual experiment. This slide shows the workflow of nucleic acid biosensor. First, after the sample loaded into the lysis chamber of our biosensor, the entire detection process starts with sample lysis and magnetic beads bending. Then the biosensor is moved forward in horizontal direction, which allows the magnetic beads in the lysis chamber to be collected and transferred through the connecting channel filled with immersible PDMIs into the washing chamber. Second, the biosensor is loaded on the ultrasonic head. And the magnetic beads in the washing chamber are dispersed and washed with an ultrasonic field. Third, the biosensor is moved to a circular magnetic array, dispersing magnetic beads in the washing chamber are separated into 6 pairs, equally by separately symmetrical magnetic force, and transferred into the corresponding reaction chambers. Finally, we put the biosensor into the heating block set at the 65 centigrade for lamp reaction. Finally, we can detect the result by visual detection or use the optical fiber model for real-time fluorescence detection. The biosensor works with assistance of a portable device. This device contains 4 fundamental elements for movement control, ultrasonic control, heating control, and real-time fluorescence detection. These 4 subsystems are controlled by an embedded microcontroller unit. To verify the specificity of our biosensor, 5 primer pairs were preloaded and dried in 5 reaction chambers. Separately, when samples with different combinations of pathogens were detected with the biosensor, only the chamber containing the corresponding primers shows positive signals after reaction. In this test, we use visual EBT lamp mixture. To evaluate the sensitivity of biosensor, several dilutions of samples were specced into lysis buffer and detected using our biosensor, and the results are plotted. The limit of detection of IB were estimated to be 0.1 copies per microliter, while that the N gene and ORF1 AB gene of SARS-CoV-2 and RNA was estimated to be 1 copies per microliter. In summary, using our biosensor, we achieve simultaneously rapid and accurate detection of multiple pathogens. I sincerely thank all teachers and classmates who have helped me from Tsinghua Medical System Biology Lab and State K Laboratory of Transducer Technology, and thank you all for your attention.